Imagine a world without reinforcement fibers. It's a world where bridges crumble easily. Buildings wouldn't stand tall, cars would be heavy and inefficient. Thankfully, that's not our reality. Reinforcement fibers are the unsung heroes of materials science. They provide the strength and durability we rely on every day. These tiny fibers work miracles when added to materials like plastics, concrete, and even our food. Think of it like adding steel beams to a building. These fibers act as tiny support structures within a material, making it much stronger and less likely to break. These fibers are the hidden champions, making our world stronger and more resilient. Whether you realize it or not, we encounter the benefits of reinforcement fibers every single day. From the durable cases of our smartphones to the lightweight yet strong components in airplanes, these tiny threads play a big role. The world of reinforcement fibers is broadly divided into two main branches, natural and synthetic. This isn't a simple case of nature versus human ingenuity. Each type of fiber brings its own unique strengths to the table. Natural fibers, as the name suggests, come from nature itself. These are fibers like wood fiber, cotton, and even spider silk, which is incredibly strong for its weight. We've been using these materials for centuries, weaving them into fabrics, ropes, and building materials. They are renewable and biodegradable, making them a sustainable choice. On the other hand, synthetic fibers are born in the lab. Scientists engineer these fibers like glass fiber, carbon fiber, and aramid fibers to have specific properties. These fibers often boast superior strength-to-weight ratios and resistance to heat and chemicals. This makes them ideal for high-performance applications in aerospace, automotive, and sports equipment. It's not enough to just have fibers. How we incorporate them into materials dramatically affects the final product. Think of it as the difference between randomly scattering straws in mud versus meticulously layering them to form a sturdy brick. One common form is chopped fibers, which are short, randomly oriented fibers mixed into a material. This is like reinforcing concrete with short steel fibers. It increases overall strength and prevents cracking. Then there are continuous fibers, which are long, unbroken strands woven into fabrics or layered into mats. These are like the steel cables in suspension bridges, providing directional strength and stiffness. Woven fabrics are made by interlacing fibers in different patterns, much like weaving cloth. These fabrics offer balanced strength in multiple directions. Lastly, we have fiber mats, which are non-woven layers of fibers held together by a binder. These are often used in molding processes for complex shapes. Each form has its own advantages, and engineers carefully select the best one depending on the application and desired properties. Section 4. A match made in material science fiber matrix compatibility. Imagine trying to build a house using bricks and jelly instead of mortar. It just wouldn't work. Similarly, in the world of reinforced materials, the compatibility between the fiber and the surrounding material, known as the matrix, is crucial. The fiber and matrix need to work together, not against each other. The matrix, often a polymer resin, ceramic, or metal, has the crucial job of transferring the load to the fibers. It's like a team. The fibers are the strong players, but the matrix is the coach that directs their strength and keeps them working together. Poor compatibility can lead to weak bonding, fiber pullout. Imagine the straws slipping out of our mud brick, and ultimately material failure. Achieving good compatibility often involves treating the fiber surface to improve adhesion with the matrix. This ensures that the load is efficiently transferred to the fibers, maximizing the strength and performance of the composite material. Section 5. Supercharging materials. The impact of reinforcements. Adding reinforcement fibers is like giving a material a superpower boost. The transformation in properties is remarkable. Imagine taking a brittle plastic and making it as strong as steel, or making concrete that's less prone to cracking. That's the magic of reinforcement fibers. Firstly, these fibers dramatically increase tensile strength, the material's resistance to being pulled apart. They also improve compressive strength, meaning the material can withstand heavier loads without buckling. But it's not just about raw strength. Reinforcement fibers also enhance toughness. This means the material can absorb more energy before fracturing, making it more resistant to impacts and fatigue. Furthermore, these fibers can improve dimensional stability. reducing unwanted expansion or contraction due to temperature changes. This is particularly important in applications where precision is key, like in aerospace components. Overall, the inclusion of reinforcement fibers results in materials that are lighter, stronger, tougher, and more durable, opening up a world of possibilities in engineering and design.